In 1835, a well-known French philosopher, Auguste Comte, stated that humans would never be able to understand the real nature of the stars, i.e. their chemical composition. But he was soon proved wrong, because luckily in the latter half of the 19th century, there was a sort of revolution in the astronomy field. Astronomers began to make use of two new techniques, spectroscopy and photography. We can say that was likely the birth of astrophysics. Together, spectroscopy and photography helped bring a new understanding of the cosmos, and for the first time, scientists could investigate what the universe was made of. They could understand how the sun was burning and what the sun was burning. This was a major turning point in the development of a newly born science, cosmology. Astronomers were able to record and document not only where the stars were, but what they were as well. But what's spectroscopy? And what's exactly astrophysics? Stay tuned and you'll find the answer to these questions and more. Let's begin. What is astrophysics? Astrophysics is a science that uses methods and principles, or we could say the power of physics, with the aim of studying astronomical objects and phenomena. Of course, among the subjects studied are the sun, other stars, and galaxies. But astrophysics also studies extrasolar planets, the interstellar medium, and the cosmic microwave background. How can scientists study these objects? How is it done? Well, they study their emissions. In fact, every object has its own emission, which we can think of as the intrinsical energy of the object that produces a spectrum. Emissions from these objects are examined across all parts of the electromagnetic range, and the properties examined include luminosity, density, temperature, and chemical composition. Astrophysics is a very broad subject, and it applies concepts and methods from many disciplines of physics, including classical mechanics, electromagnetism, statistical mechanics, thermodynamics, quantum mechanics, relativity, nuclear and particle physics, and atomic and molecular physics. That's why one has to study a lot in order to become an astrophysicist. In practice, modern research often involves a huge amount of work in the realms of both theoretical and observational physics. Astrophysicists are trying to determine the properties of dark matter, dark energy, black holes, and other celestial bodies, and the origin and ultimate fate of the universe. Theoretical astrophysics also wonders how the solar system formed and evolved, and involves the study of stellar dynamics and evolution. We said that astrophysicists study the spectrum of celestial objects. But what exactly is a spectrum? All normal matter emits electromagnetic radiation when it has a temperature above absolute zero. The radiation represents a conversion of a body's internal energy into electromagnetic energy and is therefore called thermal radiation. It is a spontaneous process of radiative distribution of entropy. Conversely, all normal matter absorbs electromagnetic radiation to some degree. An object that absorbs all radiation falling on it at all wavelengths is called a black body. When a black body is at a uniform temperature, its emission has a characteristic frequency distribution that depends on the temperature. Its emission is called black body radiation. The spectrum of a star is composed mainly of thermal radiation that produces a continuous spectrum. The star emits light over the entire electromagnetic spectrum from gamma rays to radio waves. However, stars do not emit the same amount of energy at all wavelengths. Nowadays, we are well aware of all these things, but at the end of the 19th century, physicists were unable to explain why the observed spectrum of blackbody radiation, which by then had been accurately measured, diverged significantly at higher frequencies from that predicted by existing theories. Blackbody radiation is the thermal electromagnetic radiation within or surrounding a body in thermodynamic equilibrium with its environment emitted by a black body, an idealized, opaque, non-reflective body. The concept of the black body is in fact an idealization, as perfect black bodies do not exist in nature. Graphite and lamp black with emissivities greater than 0.95, however, are good approximations to a black material. In 1900, Max Planck derived a formula for the observed spectrum of a black body. The Planckian function is a function of only the frequency of the radiation and the body's temperature. A typical Planckian function looks like this. Today we know stars can, in first approximation, be thought of as black bodies, but their observed spectrum is not an exact Planckian function. This is because, as we stressed before, black bodies are an idealization, something that doesn't really exist in nature. Here's the observed flux for a star. As you can see, it looks pretty different from the Planckian function, and it seems there are some lines missing. What caused them? This was a difficult question to answer, but then at the end of the 19th century, scientists Kirchhoff and Bunsen entered the game, and nothing stayed the same. It's time to give a proper answer to our second question. What's spectroscopy? Spectroscopy is the study of the interaction between matter and electromagnetic radiation as a function of the wavelength or frequency of the radiation. In simpler terms, spectroscopy is the precise study of color as generalized from visible light to all bands of the electromagnetic spectrum. We could say that in 1859, Gustav Kirchhoff and Robert Bunsen gave birth to spectroscopy. Bunsen reported to a colleague that Kirchhoff had made a totally unexpected discovery. He had identified the cause of the dark lines seen in the solar spectra. When certain chemicals were heated in Bunsen's burner, characteristic bright lines appeared. In some cases, these were at exactly the same points in the spectrum as the solar spectrum dark lines. The bright lines were light coming from hot gas, whereas the dark line showed an absorption of light in the cooler gas above the sun's surface. The two scientists found that every chemical element produces a unique spectrum. This provides a sort of fingerprint which can confirm the presence of that chemical. Kirchhoff and Bunsen recognized that this could be a powerful tool for the determination of the chemical composition of the sun and stars. And they were right. Astronomers and astrophysicists couldn't live today without spectroscopic surveys. The types of spectroscopy can be distinguished by the nature of the interaction between the energy and the material. These interactions include 1. Absorption spectroscopy. Absorption occurs when energy from the radiative source is absorbed by the material. 2. Emission spectroscopy. Emission indicates that radiative energy is released by the material. Spectroscopy is so important that British astronomer and chemist Warren de la Rue in 1861 stated, "If we were to go to the sun and to bring some portions of it and analyze them in our laboratories, we could not examine them more accurately than we can by this new mode of spectrum analysis." Now that we know what spectroscopy is, we can understand better how astrophysicists study star positions, masses, velocities, and all the other physical features of celestial bodies. In fact, spectroscopy provides us with positions of stars and gas clouds. For example, with the help of spectroscopy, we can understand better the spatial distribution of stars in our galaxy. Also, using the so-called virial theorem, we can infer stellar masses and chemical abundances of elements with respect to hydrogen. And last but not least, we use spectroscopy to study velocities. How do we? Well, maybe you've already heard about redshift and blueshift. Redshift and blueshift describe how light shifts towards shorter or longer wavelengths as objects in space, such as stars or galaxies, move closer or farther away from us. When an object moves away from us, the light is shifted to the red end of the spectrum, as its wavelengths get longer. By the amount of redshift-blueshift, we can infer the radial velocity of the object with respect to us. Isn't it amazing? Studying colors equals studying the universe. What does an astrophysicist do? An astrophysicist may perform research on the planets, the stars, other galaxies, and objects in the universe. They take an in-depth knowledge of physics and apply it to astrological theories. An astrophysicist may have the following responsibilities: develop astrological theories and implement research techniques to test those theories. Keep up to date with the latest research in the industry. Contribute data and research to the field. Analyze and develop programs and tools to further assist astrological research. Facilitate scientific experiments to learn more about the universe. In order to become an astrophysicist, one has to study a lot of physics, math, and astronomy. We could say jokingly that an astrophysicist studies the same physics of a physician, pretty much the same math of a mathematician, plus astronomy stuff. What are the main purposes for a NASA astrophysicist? On NASA's website, we can read, NASA's goal in astrophysics is to discover how the universe works, explore how it began and evolved, and search for life on planets around other stars. Three broad scientific questions emanate from these goals. How does the universe work? Probe the origin and density of our universe, including the nature of black holes, dark energy, dark matter, and gravity. How did we get here? Explore the origin and evolution of the galaxies, stars, and planets that could make up our universe. Are we alone? Discover and study planets around other stars and explore whether they could harbor life. Now that we know what astrophysics is, we can ask ourselves, what's the difference between astronomy, astrophysics, and cosmology? Before finding out the answer to this question, be sure to like or dislike the video so that we can continue to improve and make these videos better for you, the viewer. Plus, be sure to subscribe to the channel by clicking the bell so that you don't miss any of our weekly videos. If you'd like to help improve the quality of our content, please check us out on Patreon. We would like to say a big thank you to all those who show their support. Cosmology studies the universe as a whole and its phenomena at the largest scales, unlike astronomy, astrophysics, which study individual objects. And then astronomy is primarily concerned with observing and measuring the relative positions and paths, then giving explanations. On the other hand, astrophysics and cosmology try to explain the phenomenon observed. Usually, the students of astronomy focus on classical mechanics and optical methods to be able to observe celestial bodies and predict their positions in the sky. Astrophysicists concern general relativity and nuclear physics as two important roles to describe stars or galaxies. Cosmologists are interested in modern theories too, especially string theory, and they ask themselves why the universe was born and how. That's all for this video. Thanks for watching, everyone. Are you in love with astrophysics? Is there anything more you want to hear? Let us know in the comments below. Be sure to subscribe and see you next time on the channel.